Vulnerabilities to algorithmic complexity attacks arise in software when an adversary is able to construct an input that leads to high resource usage in either space or time. A related vulnerability is the existence of a side channel in a program, which is an unintended channel of information about a secret that is revealed to the adversary through a program's runtime or output. While an algorithmic complexity vulnerability could lead to a denial of service, a side channel vulnerability could end up leaking sensitive information. Both vulnerabilities are a reality today, whether it ranges from a denial of service attack on your Apache web server to an attacker learning your private key by remotely interacting with OpenSSL. What both vulnerabilities have in common is the need to analyze and find high complexity code. However, existing tools using recurrence relations do not handle several classes of programs with loops, because the general case amounts to solving the halting problem, which we know is intractable. Moreover, recurrence relations estimate asymptotic worst-case complexity, which may not be the observable time complexity for an attacker. To this end, we present our tool, the Time Complexity Analyzer, or TCA, as a tool for assisting an analyst in determining the empirical time complexity of a selected piece of code. Let's use TCA to empirically measure and compare two implementations of insertion sort. In my workspace, I have two fairly standard implementations of insertion sort. One implementation uses a linear search to locate the insertion point, while the other uses a binary search. TCA does not require source code, but since we are starting with source code in this example, we will first process the corresponding bytecode using soot to produce a GIMPL intermediate representation of the code. To keep things straight, let's go ahead and delete the Java source code. TCA is built on top of the program analysis platform Atlas, which produces a queryable program graph for GIMPL. While some dynamic analysis frameworks blindly instrument all program blocks or require source code to inject instrumentation during the compilation phase, TCA leverages a statically informed dynamic analysis using a loop call graph that contains the necessary information to perform a targeted dynamic analysis. During the static analysis phase, TCA recovers loops from the bytecode and determines intra- and inter-procedural loop nesting for any given entry point method. The result of this analysis is the loop call graph. The loop call graph is used by the dynamic analysis phase to instrument only the necessary program locations relevant to profiling the entry point method. TCA supports two kinds of instrumentation: loop iteration counters and wall clock timers. In this example, we use the loop iteration counter because it gives us a portable, symbolic view of the algorithm's complexity. A wall clock timer is included in TCA because counter-based instrumentation may still miss deterministic runtime characteristics, such as caching or garbage collection. TCA automatically performs instrumentation and produces a skeleton driver to exercise the program for dynamic analysis. A user may populate the driver with a custom benchmark or go so far as to integrate data from a baseline profile or automated fuzzing solution. In this example, we simply populate the driver's workload for a sort algorithm with various arrays of integers chosen from a random distribution. After populating the workload, a user may execute the driver to run the dynamic analysis. TCA automatically displays the gathered runtime information when the execution finishes. From this plot, we can see that the r-squared value indicates the slope of 1.83 is a very good fit. While linear insertion sort's worst-case complexity is n squared, we can see that empirically it is actually performing slightly better for our chosen workload. We can repeat this process for the binary insertion sort implementation if we would like to empirically compare the two algorithms on the same workloads. As expected, binary insertion sort is performing better than linear insertion sort. Okay, let's take a look at a more complex algorithm, timsort. In some cases, timsort switches behaviors of its operation to leverage either merge sort or binary sort when a performance improvement can be made. Like before, we can use TCA to profile the runtime behavior with loop iteration counters. TCA's static analysis phase reveals an interesting loop call graph for timsort that clearly shows there are three looping subroutines called from within loops from the sort entry point method, as indicated by the yellow edges from the sort method to the count, run, and make ascending, merge collapse, and binary sort methods. While the loop iteration counter gives us an idea of the algorithm's empirical complexity, we can use a wall clock timer to determine where the actual runtime is being spent in the algorithm. We select the three subroutines in the loop call graph and let TCA instrument our binary. After populating the driver workload, we see that there is a clear behavior switch when the input size is 32. While timsort itself may not be vulnerable to a side channel attack, such behavior switches have enabled side channel attacks before in critical software such as OpenSSL. Thanks for watching.